Right. Listen the Newton's laws. Newton's laws of motion. It's a very, very important concept. Whatever we are going to discuss, those things are very much helpful in the entire first year. Right. Now onwards. Right. Yeah. Newton's laws. Yeah. Till now we have seen a kinematics. That is a kinematics will have a straight line and motion in a plane we have seen. Now it is a Newton's laws next chapter. So let's understand about the Newton's laws first. Hmm. Right. So first here you need to understand the concept of inertia. Inertia. Inertia means what? Unwillingness. Inertia. Simple inertia. Simple meaning it is we can say unwillingness. Unwillingness. Don't lie. That is called as the inertia. Inertia. So here in the every body in the universe want to be always at the same state forever unless some external force is acting. So here if you have taken this body want to be same place forever until some external force act on the body. And so that means this body has a certain inertia, unwillingness. That is called as the inertia of a body. Now, as the mass of a body increases, inertia also increases. Mass is a measure of inertia. So if you have taken a heavier body, it has a more inertia. Right. So simple meaning of inertia is what tell me unwillingness. Don't like simple word we can say, simple language what we can say. And the technical meaning, so in the physics, what we can say here, the inability to change its state of rest or uniform motion or its direction. So if the body is at rest here, the body always want to be at rest only. And let us say if the body moving in a straight line, the body want to be moved forever unless some external force acts on the body. And if the body moving this direction, the body want to move in the same direction. It don't want to change the path. Yes. So here inertia we have three types. We have what is one we can call inertia of rest, inertia of motion, inertia of direction. Inertia of rest means what? Unwillingness to change your state of rest. And inertia of direction. Yes, unwilling to change its direction. And inertia of motion means what? Tell me now. Unwillingness to change its state of motion. Right. So here inertia of rest. Inability of a body to change its state of rest by itself. It doesn't change itself. अपने आप को change नहीं करेगा. So then to change, we need to apply certain amount of external agencies required. Right. Inertia motion. Yes. Now the example if we see here, yeah, understand first. Yes, when the bus starts suddenly, what happens? You tell me now. When the bus started suddenly, so that means whoever bus, now the man is standing. Just imagine. Bus, so the man doesn't know bus is moving. So then what happens? You tell me now here. Look at now. The bus started and bus is moving. Bus moves, then lower part of a body is in contact with the bus. As the bus moves, this lower part also will move. But this upper part of a body, so it will be rest only now. So as a result, what happened to the body in a person now? Will move, will fall backward. You can imagine now here. Bus started, lower part of a body which is in contact with the bus will move forward. But this upper part of a body doesn't want to change now. So it will be move forward, backward. Next, if the bus suddenly stops. Let a bus is moving, suddenly stops. That means what happens now? So here the yes. Now what happens now? Bus is moving. That means the upper part of your body, it will always want to be motion. It is motion. But when the bus stops, then lower part of your body, which is in contact with the bus, it is stopped. But upper part of your body move forward now. That's why the passengers will move forward. And so you might be seeing this is when the bus is taking the right turn and left turn. So if you observe here, when the bus is taking the left turn, the passengers on the right side they will move. Yeah, that is what tell me now. The person, the body is tuned to take just to move in a one direction. So, but the bus is taking the some other direction now. Direction it changes. The body doesn't willing to change its direction. That is called as the inertia of direction. Understood? So the body. So in the universe, any body. So here want to be in the same state forever. Like you might be seeing here, and until your father or mother will shout, you want to be sleep forever, isn't it? So what your state now here? So you want to be at in the on your bed only forever until your mother shout or father shout. Yes, that is the inertia. Mm. Mm. So you will, as of now, you just copy the headings and all. So then I'll share the notes now. Then you will complete the notes. Briefly, you can copy. After sharing the notes, you can copy complete. Headings you need to honor here. Inertia means it's not like a value we can say. So this is what tell me now here. Measure of inertia we have now. That is a we can measure the inertia, how much inertia it has with the mass we can measure. Basically, inertia is what we can say now that is not a numerical value. Okay, so yeah, so here that is a nature. Uh, this is an objective. So this is not a, we cannot say this is a number quantity. Uh, right. Then now let's understand this thing here, basic phenomena. Right. So here let's talk about the Newton's first law. And what the Newton's first law is nothing but is also called as law of inertia. As we have seen now, the same thing here. So what should be now? Every body continues to be in the state of rest or of uniform motion in a straight line unless it is compelled by an external force. Unless no force acts on a body, the body want to be at rest or it will move in a uniform motion in the same straight line want to be moved unless it is compelled by an external force. That is a Newton's first law. Newton's first law is also called as the law of inertia. Right. And Newton's first law will use the property of inertia. Will use property of inertia, and definition of force and mechanical equilibrium. Mechanical equilibrium means what? So we can say now here this body is at rest. That means the body is in mechanical equilibrium. Mechanical, it is mechanic, that word comes under the motion. Equilibrium means at rest. It is a mechanical equilibrium. Then we have the different type of equilibriums. We have thermal equilibrium, mechanical equilibrium, electrostatic equilibrium we have. So here we should consider the if the body is, there is no motion related, we can call it as a mechanical. Thermal equilibrium means if the temperatures are same, then we can say thermal equilibrium. Electrostatic equilibrium we have, that is comes under charges. Positive charge, negative charge, we have charges related to the term. Here we should call it as a mechanical equilibrium. Right. You don't worry, I will share the notes. Notes I will share regularly. Share to your father. Thing. I'll see that. I saved your father number. Okay. Yeah. Right? Right. So, fine. I'll share the notes. Don't worry. So now let's see the next one here. Newton's first law we have seen the next one here. We'll talk about the Newton's. Yeah, force we'll talk now first. Before that, now here force. What the force means? What tell me now? The one which tries to change the state of the body, that is called as a force. The one which tries to change, which changes or tends to change the state of rest or state of motion is called as a force. Which will tries to change. That we can call that physical quantity is called as a force. And we should talk about two types of forces. One is called as a contact force. The other one is non-contact force. And contact force means what? Tell me now. So the two bodies are physically in contact. We have, so here we have the body here, and this body is physically in contact with this thing. This body pushes. That is called as a contact force. Next, there is the other type of forces, non-contact force. If we have a body is in the gravity, so we have a body in the air, it will experience certain amount of pull. Yes, now here, so then the gravity will attract the body to downward direction. Now there is no physical contact, but still we have a force is there. Those are called comes under non-contact force, electric force between two charges. We have force between two charges, magnetic force. We have two magnets we have taken. Even though there is not, they are not in physically contact. When I kept these two nearby, they will experience a force. That is a magnetic force. All those are comes under non-contact force. Yes, electrostatic force, that is magnetic force, gravitational force. These are comes under non-contact force. Right. Next. So let's talk about the momentum. Momentum. Here we should call that momentum is two types of momentums are there. Linear momentum and angular momentum. Here in this center Newton's laws, momentum is linear momentum. Okay. So linear momentum, how it is defined as linear momentum. Let's understand first. Linear momentum will denote with a letter of P, which is a vector quantity, and which is defined as the product of mass into velocity. Product of mass into velocity is called as the linear momentum, m into v, and where m is a mass and v is a velocity. Now, so can you tell me the units now? What will be units? And yeah, so momentum is a vector quantity. And what the SI unit, tell me now? SI unit, and which is equal to kg meter per second. CGS unit, gram centimeter per second. Momentum is a vector quantity. Right. Momentum means what, tell me now? Which is the product of mass into velocity is called as a momentum. If any body is in motion, it has a momentum. Right. Every moving body has momentum. Any surface, any direction. If the velocity is there, means it has a momentum. Next, let's talk about change in momentum. Change in momentum means what? Tell me now. Change. So we have initially we have some momentum, after some time some other momentum. Let us say body mass. We are talking about the same body mass is m, and velocity v1 is the initial velocity and v2 is the final velocity. Then we'll talk about the change in momentum. So tell me now, initial momentum, which will be given. Momentum means what will mass into velocity. Initial momentum is what we can say now, mass into initial velocity now. We can say v1. Next. And this is p2. We can say now m into v2. Now we'll talk about change in momentum. Change in momentum. Change in momentum. So this change in momentum, we can say this as delta P, we can say. Change in momentum is delta P, which will be equal to final momentum minus initial momentum. Change, we can say delta, we can indicate. So that is delta P, which will be equal to final momentum m into v2 minus what, tell me now, m into v1. So that means we can write it as delta P, and which will be given as what we can say now, m into V2 minus V1 we can write now. So that's why we can say now this is delta P, which will be equal to m into m is a mass, and so we can say V2 minus V1 we can write as delta V, where the delta V is the change in velocity. Delta V is what we can say, change in velocity. Okay. So momentum, change in momentum equal to what? M into change in velocity. Now let's see this thing here, change in momentum calculation, different situations. Right. Done. Now let's see the first case. Hmm. Change in momentum calculation. Right. Now see this thing here. Copy it now here. So here case 1, a body of mass m moving with a velocity v hits the wall and comes to rest. In this case, we need to find the change in momentum. Initially, we have a body, a mass m, mass of a body is m, mass of a body is m, and which is moving with a velocity v. Yes, so this means that velocity v1, which will be equal to v, it is moving downward direction. And it will hit the surface. It will hit the surface. After hitting the surface, now the final velocity of this body becomes zero. Right. In this case, they are asking to find what will be the change in momentum. Yes. Change in momentum, just now we have seen na, that is given as what, tell me now, mass into change in velocity. Now tell me now here the initial velocity is how much, you tell me now? V, and we use the vector notations. It is moving downward direction now. So that's why we have taken as minus j cap. And the V2 final velocity is how much now? 0. Now change we need now here. So the delta V means what, tell me now? Change in velocity, that is given as V2 minus V1. So this value how much now here? 0 minus minus plus na, plus V into j cap. This is a delta V. So that means we need the delta P na, change in momentum. Delta P, which is equal to what, tell me now? M into delta V. Delta P is equal to M into delta V. So that means from this we can write it as delta P, and which will be equal to m into delta V. We have what, tell me now, V into J cap na. So from this we can get the magnitude of change in momentum. How much you tell me now here? This is m into V. This is the change in momentum magnitude. Right. Here the final velocity is zero. That's why same formula we got in this case. Final velocity may not be zero all the cases. No. Right. Next one. Now in this, see the second case now here. Second case you tell me now. Now a body of mass m moving with a velocity v hits the wall and rebounds with the same velocity. Okay. So briefly you can copy the complete notes I'll share now. So thereafter you can prepare your notes. So briefly, for your understanding purpose, you can prepare. Mathematical part you note down carefully. So this mass of a body is m. So here, tell me now here this body moving with a velocity v1, which will be equal to v. What they are saying here, it will hit the wall, rebounds means what, going back. Rebounds with how much velocity? Same velocity. Rebounds with the same velocity. That means v2, which will be equal to v only na. After hitting it is moving upward direction with the same velocity is moving. Now in this case, we need a change in momentum. Yes, so tell me now, we can use the vector notations now. Initial velocity v1. How much the v1 you tell me now here? That is v into what we can say in a downward direction minus j cap. Next v2, and which v is equal to what, tell me now, v into what, tell me now, positive direction na, plus j cap. After hitting it is moving upward direction. Upward direction means positive only na. Now tell me now, change in velocity now. Change in velocity. What we can say, tell me now here. V2 minus V1. Yeah, tell me now V2 minus V1, how much will come? V2, that means what, tell me now? V into J cap minus or minus plus V into J cap. Then how much will get the delta V, tell me now? Yes, 2V into J cap. This is a change in velocity. Right. Now from this we can get the change in momentum. Well, change in momentum, you tell me now here delta P, which will be equal to M into delta V na. So that means what we can say now, 2mv into J cap. So that means what the change in momentum in this case now? Change in momentum, which is equal to 2mv, and so that is which direction? Positive y direction. J cap na plus J cap. That means it is along the positive y directions. Right. Next. Now see the next one. In this case, what happens now here? Body moving with a velocity v1 hits the wall and rebounds with some other velocity now. That means the initial velocity, final velocities are not same, that's it. Okay. So you can tell me in this case, so then this is the velocity v1, and after hitting moving with a velocity v2 upward directions. Now we can use the vector notations now here. v1. vector. So this will be given as what we can say now, minus v1 into j cap, we can say now downwards. Next, v2 vector, you tell me now. And that should be equal to v2 j cap. Now we'll see the change in velocity. Yeah, tell me now, change in velocity means delta v. Change in velocity delta v, and which is equal to what, tell me now, v2 minus v1. So that is delta v, and which is equal to, so this is v2 minus the minus v1 na? Into what you tell me now, j cap. Now from this, change in momentum delta p, which will be equal to m into delta v. So that is what we'll get now here, delta p, that is m into, we can say this as v1 plus v2 into j cap. So that is magnitude of this change in momentum. That is m into, we can say this as v1 plus v2. Understood how to do it? Yeah. Now, so let's understand. We have in these cases the ball hit and will move upward directions. Now you might be seen now here. You might be observed when you throw the ball like this, it will hit and again will come back to the hand. But we have thrown with some angle. What happened? Again, it will move with some angle. Okay. So that we are going to see now here in this case. Now, next case. Now, in this case, a body of mass m moving the velocity, initial velocity u, strikes the wall at some angle, theta with the horizontal. It will hit the wall and it will move with the same velocity. Right. This we are going to analyze now here. Initial velocity u, let us say, whatever it may be, velocity given, u given. And just imagine now, this is something wall we have like this. And it makes some angle. So this angle, they give an angle with where you tell me now horizontal, that's why x-axis angle. They given a vertical angle means y-axis angle we have to consider. So this velocity they given as u. After hitting, it is moving like this. And so with the same velocity. Now here, whatever the angle before hitting, after hitting also will maintain the same angle, remember. This angle is also theta. Right. Now in this case, what we need to do here? So this velocity is not along x or y direction. So we have to resolve it in this case. Earlier with the resolution we did now, that concept we need to apply here. So look at now here. This is one and this is the other one. Yeah, you tell me now here. In this case, this angle is theta. That means this angle is how much now? Theta. So this angle is theta. So we resolve the u into components or not? And what we can say, this component is a u cos theta. And this is what, tell me now, u sin theta. Right. Same thing we'll do final velocity also. And we draw the lines, parallel lines to x-axis, one line, and y-axis, one line we have drawn. So you see this angle is theta. That means this angle is also theta only, na? Yes. So tell me now, this velocity is now here. This is u cos theta. And this is what, tell me now, u sin theta. Now we can write the initial velocities now here. Initial velocity we can say now v1. Tell me now v1, it has a components. X direction we have a u cos theta, na? U cos theta into I cap minus u sin theta into j cap. Check it all of you. Next, funnel velocity v2 I can write, tell me now. And this is equal to what, tell me now, u cos theta into I cap my plus now here u sin theta into j cap. Check it. See the directions now. This is v1. Now this is v1. This is v2. Before initial velocity v1. Okay, after hitting v2. Now we need to find the change in velocity. Tell me now, change in velocity means what? v2 minus v1 na? Change in velocity. That means what we can say now, v2 minus v1. We need to subtract these two. Tell me now, if I subtract now, which will get cancelled, which will be left out? Tell me. U sin theta will left or cancel? Will remains. Yes, now cos theta will get cancelled now. So that means what will come? Plus will come or minus will come? Check it. Check it. Plus. Yeah, plus 2u sin theta into j cap, isn't it? Now from this, can you tell me now change in momentum now? Yes, so the change in momentum now here, simply multiply with m, say, that is m into what we can say now here, delta v. So that is what we can say now here, 2mu sin theta into j cap. So if I say the magnitude means how much this value, that is 2mu sin theta. And the direction means what direction now? Positive y direction. Right. Sometimes they will give the angle, the vertical also they will give. Y-axis angle will take. Then we have to simplify. Now let's see the next one. Projectile motion, the change in momentum of a body between highest point and point of projection. Highest point and point of projection. So recollect the projectile motion once again. Now this is O. We have taken A is the highest point and B we have taken as a point of projection we have taken. And this A is highest point. If we have remembered, this is the velocity we have considered. With a velocity we have thrown, right, this velocity u we have thrown now here this angle and which is equal to theta, and now we resolve into components now. This is equal to what, tell me now, u cos theta, and this component is what, tell me now, u sin theta. Okay, now here we need to find the, in the O and A points we need to see. At O point, how much the velocity, that velocity will called as initial velocity. Can you tell me now? At O point, what is the velocity now here? V1 we are calling. That is a velocity at O. Why 0? Yeah, we have to some velocity. That is how much now? It has not in one direction now. So it has two components are there. So what we can say, tell me now, U cos theta into I cap plus what, tell me now, u sin theta into j cap. Now when you're coming to the point B, A, now tell me now here, this is the velocity at where, you tell me now? This is the velocity at the, yes, at A, what O point, this one. This is the velocity at O. Velocity at O. Now tell me now, velocity at A, velocity at A. If you remembered, at the highest point, so only the horizontal component of velocity only left. Vy value 0 na. Velocity goes on decrease. Finally, at the highest point, vertical component of velocity is 0. But horizontal component of velocity always remains same only. So that velocity v2, that is equal to what, tell me now, u cos theta. And this is I cap. Horizontal component of velocity does not changes. Only the vertical component of velocity decreases. At the highest point will become 0. Yeah, tell me now here in this case, change in velocity. Now what is change in velocity? Tell me now delta V now. V2 minus V1 now. And so which will get cancelled now? So that is u cos theta will get cancelled. So that will be equal to what, tell me now, minus now. Minus u sin theta into j cap. So that means from this delta P, so the delta P, which is equal to what, tell me now, m into delta V. So that's why delta P, which will come to be what, tell me now, minus m u sin theta into what, you tell me now, j cap. So that is mod of delta P, and which will be equal to what, tell me now, mu sin theta. Okay. So this is the change in momentum from the point of projection to the highest point. Now, if they are asking the change in velocity momentum from the point of projection to the striking point means point B. We need to see the velocity difference at O and A. O and B. Okay. So tell me now this thing. Fast, fast. Next, now tell me now here, change in momentum between where to where now striking point and point of projection. That means at O and B we want. Yes, now here at the point O, what is the velocity? Tell me now. Ah, velocity at point O. Tell me now. Ah, same thing. Yes. Velocity at point O. That means this velocity will call as a V1. How much this value? Tell me now. U cos theta into I cap plus what? Tell me now. U sin theta into J cap. And whatever the velocity at point B. Point B. That means how much the velocity? U cos theta remains constant. U cos theta into I cap minus U sin theta into J cap. Same velocity, but it is in a downward direction, opposite direction. At the point B, if we see this thing, velocity, this is Vy is downward direction, and this Vx is this direction. This is Vx. Vx, it will be same as Ux only. Horizontal does not changes. But whatever the velocity at point O vertical, this U sin theta upward direction, but here U sin theta is downward direction here. Here this is U sin theta, which is downward direction. Okay. Now change in velocity, tell me now. Yeah, so this it will be when the body moves up, again will be reaches the highest point, velocity zero, again will come back now. Then what is the velocity direction? Downward directions. Hmm. So tell me now, change in velocity. What is the delta V? Tell me now. That is V2 minus V1. So tell me what will come now, which will get cancelled, cos will get cancelled. We have sine terms we have now. So that is delta V, which will be equal to minus 2U sine theta into J cap. From this we can find the delta P. Delta P, which is equal to M into delta V, and which will be equal to minus 2mu sine theta into J cap. This is the change in momentum. Yes. Understood now here all these cases. Now, look at now here in this case. A particle of mass m moving with uniform speed v in a circular path of radius r. As it moves from point A to point B, such that arc AB makes an angle theta at the center. In this case, they ask him to find the change in momentum. This similar thing we have seen earlier, that is change in velocity case we have seen. Change in velocity in case of circular motion. The same thing will repeat again. If we remember, and this is point A, and let us say this is the point B. This is the point B, and this is the point B. So at this point B, this velocity V2. And what they're saying here, at the center of the arc, it is making some angle, these points. This angle is something theta. Now they are asking to find the change in momentum. Here, if you see here, this is what type of motion is a uniform circular motion. Uniform circular motion means what element of velocity is same only. Yes, magnitude of velocity is same, but directions are changes continuously. That means speed is same, we can say now. So this is mod V1, that is mod V2, both values are equal. That is equal to V only. Mod V1, mod V2 equal to V only. Now, in these cases, if we remembered, we have seen change in velocity delta V, that is V2 minus V1. We have seen now by using parallelogram law, we have seen now that is equal to 2V sine theta by 2. Remember this formula? Change in velocity 2V sine theta by 2. By using parallelogram law, V1, V2 values are same only now. Yeah, so this is delta V. From this we can say now delta P. For the delta P now here, this is M into delta V, and that is given as 2mv into sine theta by 2. 2mv sine theta by 2. This is the change in momentum in case of uniform circular motion. Right, next one. Newton's second law. No, these are the momentum, this concept. Newton's second law based upon the momentum. That's why we have understand the momentum first. Okay. Now see this thing. What is the Newton's second law is the rate of change of linear momentum is directly proportional to force. So that means Newton's second law, that is given as what will be now F proportional to what will be now dp by dt. F proportional to dp by dt. So we are using a one proportionality constant now. Proportionality constant K. That K into dp by dt. K is experimentally determined, the K value as a 1. K is determined experimentally, that is K value is 1. So from this we can write this as F is equal to what, tell me now, simply dp by dt. This is moment of definition, yeah? Right. So that is F is equal to what, tell me now, simply dp by dt. And this we can be also written as F is equal to dp means we can say change in momentum. That is delta p by delta t. Okay. This can be also written as change in momentum delta p by delta t. F is equal to rate of change of linear momentum. Differentiation is nothing but change. Now, so from this, when you are coming to here, F is equal to what you tell me now? We can say this as dp by dt. So that is equal to what we can say now? Here, P. What is the P which will be given us? What tell me now? So this momentum now here, this can be written as what we can say now d by dt of P momentum which is given as m into v, m into v. Now we need to differentiate now here. While differentiating, we have to take it as u into v rule. So if I say m is so generally most of the case m is constant. Some case m is also variable. The m variable which case will happens in case of a rocket launching case, mass is variable. When the payload will releases, in those cases mass of a rocket will decrease now in those cases. So if I say this mass is constant, then we can write as what will be now m into we can say dv by dt, this relation. So in this relation, when can be applicable? If m is constant. If m is not constant, we cannot do this thing. And then from this, we can write it as what tell me now f is equal to v is a rate of change of velocity. That is nothing but what tell me now a. So we can get it as what tell me now f is equal to ma. dv by dt is nothing but a now. That's why f is equal to ma. Right. Now here, let us consider here m is variable and v is constant, let us say. Then what I will do, tell me now? Then in that case, v is constant. So here, if v is constant, in this case, what we can write now here, f is equal to this is dm by dt into v. Right. And our 99% of the problems based upon the m constant. Okay, in this based upon this relation we can use. And only the 1% of the problems based upon the v constant, m is variable. Okay. And so only in the rocket launching cases, only the m is variable. Remaining all cases, m is constant. Okay. Fine. Okay. Yeah, that's it. We'll continue next. So I'll confirm it. Mostly, yeah, we have. I will let you know most probably. So I'm